Well, we can talk about that. Yeah. That's what I was. All right. All right. 1.3 limits at infinity. So we've already had infinite limits. When we talk about an infinite limit, we're talking about the limit being infinity. And so far that's happened at a vertical asymptote, right? Do your math homework. When the limit is infinity, the limit doesn't exist. In this case, we're talking about a limit at infinity, which would be as x goes to infinity, or as x goes to negative infinity. So these are, by definition, one-sided limits, right? By definition, you cannot approach positive infinity from the right-hand side. It's really, really hard to get on the right-hand side of infinity to come back towards, right? It doesn't work. So if you're ever heading towards infinity and you see a guy coming back the other way, that should spook you a little bit, right? Like yesterday upon the stairs, I met a man who wasn't there, and he wasn't there again today. I think he's from the CIA. Anyway, this is the end behavior. Yeah. Wah, 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 wah.
Is it supposed to be a joke or just a rhyme? Amen.
Either one or both or neither. I don't care. It doesn't matter. No, it wasn't there. I really didn't meet a man who wasn't there. This is looking at the end behavior of the graph. Okay. And end behavior is predictable. End behavior is very predictable. So we're going to spend most of the year learning about local behavior. Local behavior is all the stuff that happens for relatively small values of 0. That's like increasing, decreasing, local max, local mins, x-intercepts, y-intercepts, all that good stuff. End behavior is relatively boring. If you were to like zoom out on a graph, you would lose all the fine detail centered near the origin, and you would just look at overall trends, okay? So that's essentially what we're going to be doing. We're going to be analyzing it, though. We might zoom out on a couple just to kind of see what they look like. But there's really very few things, like you're limited. Let's just say as x goes to infinity, what are some of the things the y values can do? Well, they could increase without bound, right? Like x squared, e to the x, etc. They increase without bound, or they could decrease without bound, right? Such as, you know, negative x squared or others, right? This is as you go way out. What else could they do? Those are kind of the two boring ones. Very good. Those are the ones that are really, really interesting. You could have something tapering off like this towards a horizontal asymptote. Yeah. Now, you can actually have a horizontal asymptote that looks like this. Believe it or not. A horizontal asymptote is an asymptote, but it's not a discontinuity. You can actually cross a horizontal asymptote, and we'll meet a guy in here that crosses it infinitely many times. Horizontal asymptote just says the y values are predictable, right? You can predict that they're approaching something, tapering off towards something. And so that's kind of cool. We can also have like no end behavior at all. You know, that would be like if we have the graph of the natural log of negative x, it has a vertical asymptote on the y-axis, and it looks like this, right? It doesn't have any right end behavior. It has left end behavior. It goes to infinity, but it doesn't live to the right of 0. So when we're talking about the right end behavior of the graph, we're talking about the limit as x goes to infinity, not the rightmost point of a graph. Very important to make that distinction. And then there's one other thing it can do, really. I mean, it can oscillate, like sine, right? Oscillate. And it can oscillate between two fixed values like that. It can oscillate like this up here between two smaller and smaller values, which is horizontal asymptote. And I'm not going to draw it because it's hard, but it can also oscillate between two increasingly large values, right? Eventually going up to negative infinity and down to positive infinity, and then down to negative infinity before it turns around. Blows your mind if you think about it. Don't. So Yeah, that's pretty cool. Now you're going to see that when we analyze end behavior, we're going to be able to do it pretty quickly because a lot of the things that affect the graph locally we can disregard. All right. For instance, if we have something like this, the limit as x goes to ocho borracho, right, or drunken 8, which is another name for infinity. That's what his friends call him. They tease him about it. Yeah, he's all right. That's a 5th degree polynomial. All of those terms have something to do with the graph, but there is one term more than all the others as x gets really big, no bigger than that, no bigger than that even, will dominate the growth of the problem. Which term is it? X, yeah, x to the 5th, the 3x to the 5th. We call that the leading term, not because it's in the front, which sometimes it is. Of course, we call it the leading term because it has the largest exponent on the variable. 3 is called the leading coefficient. Yeah, so if we're analyzing the limit at any other value, besides maybe negative infinity, all of those other values are going to be important. But when we look at the limit as x goes to infinity, we don't even really need to look at anything other than the leading term. Because as the leading term goes, so will the rest of the function. So what happens to 3x to the 5th as x goes to infinity? It goes to infinity, yeah. Now, College Board does not like you doing this. If you work straight down and you do this, 3 infinity to the 5th, they don't like that. People will have heart attacks if you just throw infinity in there as if it were a number, right? Math purists. So don't do that. But just tell yourself in your head, what's a huge number to the 5th power? A huger number, right? What's a huger number times 3? A huger number, okay? Because the infinity is really a destination. So huge, huger, huger. This thing is approaching infinity or DNE, right? That's still an acceptable answer. What? Yeah. So what would the limit be on the same function as we approach negative infinity? Also DNE, right? What would be a better answer? Negative infinity. Good. Because again, if you plug a negative number into that, because it's an odd power, a negative number to the 5th is a negative times 3 is negative. Yeah. So these have opposite end behaviors. And what this graph kind of looks like is it comes in from the bottom and it goes out the top. And you'll see later on that because it's a 5th degree polynomial, it can have up to 4 turning points like this. So this right here is what the local behavior would be. And local is kind of a relative term, relatively near the origin, right? The values could still be like from, we can have that local min on the far right still occurring like at x equals 100 or even 1,000, which dwarfs still by comparison to infinity. So that's still the local behavior. But if you were to graph this function, in a relatively small window, negative 10 to 10, you might see some of this stuff. But if you were to keep zooming out, you would not see that. It would start to look more and more like what we call the end behavior model. It would look just like this. You wouldn't even really see it. It would look something like that. And then this right here would be the local behavior, right? In other words, the graph of the entire function begins to look more and more like 3x to the 5th. Because by comparison, those other terms that I scratched out, they're contributing to the value, but as x gets larger and larger, their contribution is felt less and less and less. Okay, so maybe so. All right. How about this one? What's the limit as x goes to infinity of e to the negative x? Well, when you plug in, it will become, yeah. You either know, thank you. You either know what the graph looks like, and then you can okay, or you can do the same thing we just did. Don't plug in infinity right below it. If you want to do it off to the side, you can. But If you plug in a huge number, you have negative huge, right? E to the negative huge. E to the negative huge. Well, let's do that. E to the negative infinity off to the side. That's over 1, right? Bring that to the bottom. That's 1 over e to the positive infinity. Now remember, e is the natural base. It's like 2.7, so it is exponential growth. What happens to the denominator? It's about 3, right? 3 squared, 3 to the 4th, 3 to the 100th. That's getting bigger and bigger and bigger. What happens to a fraction when the top stays a 1 and the bottom explodes? What happens to the fraction values? They get smaller and smaller and smaller, approaching what? 0. Guess what this limit is? It's 0. And so that's the nice thing about infinity. You can look at trends, right? We're approaching positive infinity, but when you plug in, it becomes negative infinity, which is 1 over e to the positive infinity, and now it's approaching 0. We're going to look at this later on. In fact, anytime you have a fraction where the denominator grows faster than the top, whether the top grows at all, the top could be growing, but if the bottom grows faster than the top, the ratios will still approach 0. It's not a race. The bottom will outpace the top, eventually pulling it down towards 0. It'll never equal 0. It'll only approach 0. Now, what's the other side? What would be the limit as x goes to negative infinity? I don't know. Well, let's see. We're approaching negative infinity now. When you plug in a negative, you get negative infinity. That's positive infinity now. What is e to the positive infinity approach? 3 squared, 3 to the 4th, 3 to the 10th, 3 to the 100th. That's getting big, right? Those are like powers of 3, essentially. That's getting huge, approaching infinity. Positive huge. Or DNE. Now, I know y'all remember what the graph looks like. E to the x is your parent function. It looks like this. When you replace x with negative x on any function, it reflects it across the y-axis. That's a real quick review. So here is our function that we're looking at. When you replace x with negative x, it reflects any function across the y-axis. So if you know what e to the x looks like, it's the purple nurple graph. Now you can just be like, oh, as we go to the right, it's leveling out, approaching the x-axis, which is 0. As we go to the left towards the negative infinity, it's increasing without bound towards infinity. This is a very important problem because exponential functions are kind of unique because they have drastically different, I'm going to write that, drastically, if I can spell it, drastically different end behaviors. And I don't mean like negative infinity and positive infinity, like x cubed and x to the 5th. I mean, on one hand, they increase or decrease without bound, but on the other hand, they taper off towards a y value. Okay, whatever the horizontal asymptote is. That's important. All right. But again, you don't need to know what the graph looks like because you could do your analysis just by plugging in huge numbers and looking to see what the ratios do. All right. Sine of x as x goes to infinity. Is sine of infinity an acceptable answer? No, in fact, that causes heart attacks, right? So just think about the graph of Sahala as you go out to the right forever and ever. It's going to oscillate between 1 and negative 1, 1 and negative 1, 1 and forever and ever and ever. Are we ever going to stop oscillating? No. So is there any limit to what the values are going to be? It's got to be D and E. All right. Now, if you use the word limit outside of math class, someone might argue, well, there's a limited number of y values it takes on. And you're like, no, there's not. There's infinitely many, right? But it is bounded. Maybe that's what that person meant. It stays bounded between negative 1 and 1. But that's something different. That's not what we're talking about. We're talking about as x goes out to the right forever and ever, what are the y values doing? Right? They're not increasing without bound. They're not decreasing without bound. They're not tapering off, predictably going towards one specific value. They could be any of the infinite numbers between negative 1 and 1, you know, whenever you take the pulse. And then it keeps going. All right, so here's an interesting one. Now we're going out to the left on sine of x times x. Now this one, if you use direct substitution, you're going to get negative infinity times d n e. That's not necessarily d n e. If you have more than one function and you get d n e, you kind of have to analyze it differently. So here's how we can think about it. Think of x as being the thing that's in front of the sine function. Over here, it was a 1, and so this oscillated between 1 and -1. We call that the whatlitude. Amplitude, right? It oscillates between 1 and -1. Here we have the amplitude that's defined. There's my crazy love of L's again. The amplitude is increasing as x increases and vice versa. So if you think about what the line y equals x looks like, and the line y equals -x, like this, here's what this graph looks like. It starts off like this, and then as it oscillates, it does this. This is the one that's going to continue to oscillate, but as it does, the amplitude is increasing, bounded by the curves x and -x. What's happening as we go out to the left? It's oscillating between two increasingly large values. So what do you think, bless you, the limit is? Yeah, it doesn't exist. Not because it's infinity, not because it's negative infinity. It's kind of like oscillation between two fixed values, except this one, whew, it gets even worse. And this one, if you think about for a while, will kind of blow your mind, because as you go out to the left far enough, it's going to get to a point where before it turns around to go down, it's going to go up so high towards infinity that you can wait there forever and never see it turn around before it finally does turn around and goes back down towards negative infinity, at which point you could stay there forever to wait to see where it turns around, and you'll never see it turn around because it's going down so low, but it will eventually turn around and bounce back up towards infinity. That's weird, right? That's weird. So it's definitely d n e. Now look at this guy, 1 over x sine of x. 1 over x sine of x, also known as sine of x over x, but when we, or over x. But when we write it like this, now when you plug in, you get 0 times d n e. 1 over infinity is 0 times d n e. That still could be anything. What's happening to the amplitude now? They're getting smaller and smaller. Yeah, so if you want to see what this graph looks like, sketch the graph of 1 over x, which it's another parent function. It's your reciprocal function. It looks like this and this. This is 1 over x. And then you look at the reflection, and it looks like this and this. And now the graph of this function looks like the following. It's still oscillating, but it's doing this. And as it goes out to the right, it's oscillating by less and less above and below the x-axis. So it looks like it's going to become the x-axis, but if you were to zoom in anywhere down the line right there, guess what it's going to look like? That. You're going to be able to, you know, in theory, zoom in and still see space above and below. But guess what the limit is here? It actually is 0. Yes. Because the y values, although they never stop oscillating, they are getting closer and closer to 0 in the sense that they're oscillating by less and less above and below 0. So you'll see later that this is the definition of a horizontal asymptote. If either one of the end behavior limits equals a finite y value, by definition, there's a horizontal asymptote at y equals that y value. So this is a horizontal asymptote. Can a graph cross its horizontal asymptote? Yes. In fact, this one does it however many times. How many times? Infinitely many times. I used to ask, instead of crosses, I used to ask, can a graph touch its horizontal asymptote? And the answer is yes, right? And this one touches itself how many times? Yeah, and that's not the right way to ask it either. But I was, you know, back then I was stupid. Still am. Yep, my Apple Pencils. It touches its its own asymptote. This one touches its asymptote how many times? Yeah. Dude, quit touching your asymptote. Leave your asymptote alone. Yes, because it could be anything between -1 and 1. The limit is only going to exist if it actually is a single specific y value. And because it's never going to stop being anything between -1 and 1, it's not a specific value. Okay, so this type of function here is kind of an interesting, exceptional type of function. Most of the time, we're interested in, was that the bell? No. We're interested in the horizontal asymptote. All right. I think I'm still hearing the from the bologna sandwich in my ear. All right. Hey, speaking of definition, we define discontinuities with limits. Now we can define other types of asymptotes besides vertical with limits. This is an if and only if statement, so it's a definition. It goes both ways. So if the limit as x goes to infinity is L, or I should say, the limit as x goes to -infinity equals L. L doesn't even have to equal each other. Let's do this. Let's amend this. L1, L2, where L1 need not equal L2. But they can, okay? You can have at most 2 n behavior limits being different values, right? Because there's only 2 n's. But it only takes one of them to exist, like in the case of e to the x, for the following conclusion. Then f has a horizontal asymptote, which we can abbreviate, until May 9th as an HA at y equals L. Now it's an equation of a line. So just like a vertical asymptote is x equals, horizontal lines are y equals. So here's some examples, examples. You have y equals 1 over x. This one has a horizontal asymptote at y equals 0. Oops. And of course, we've already seen it. It approaches the same asymptote on both ends, one from above, one from below. So here's an asymptote that affects the graph on both ends. You can have another example. Let's look at e to the x, right? We've already seen him, but e to the x has a horizontal asymptote on the x-axis, but e to the x is only affected by it on the left-hand side, okay? And you could still draw it if you want, going on both ends. And then we have another example that is going to become a parent function. Y equals arctangent of x. He'll show up later in the year. And here's what he looks like. Arctangent of x has 2 horizontal asymptotes, one at pi halves, one at negative pi halves, and it approaches one of them as you go out that way and the other one as you go out this way. Oh, okay, cool. Lunch, yeah. Later in the year, right, like after lunch. Okay, cool. So you might want to memorize it now. Now, I don't know if Mrs. Skurhawk and Bill Credit got to the inverse trig functions last year. Hopefully she did. So it's, yeah, okay, good. This is the only inverse trig function you have to memorize, arctangent. Right? Now, you can't have 3 horizontal asymptotes because there's only 2 ends to the graph, left and right. It works the other way, though. If you know a function has a horizontal asymptote at y equals L, then you know at least one of the n behavior limits is a finite y value, possibly both, and possibly the same number, but possibly different numbers. All right, have a great lunch.